Now we're going to talk briefly about the SMP operating system. Not a whole lot, but we're going to let operating systems handle the details. But I do want to talk about some basic issues. First of all, whenever you power up the Raspberry Pi, we've talked a little bit about how the GPU is what actually is going through and checking, is doing all the boot up. It's examining the BIOS, running the initialization code out of the BIOS, and then once it's done with the initialization of the board, and the board is up and ready to be run, it then transfers control over to one of the processors, CPU 0. And it does this by pointing it at an address where the operating system is contained, so that that CPU, that core 0, can go ahead and start running the operating system. Now, if there's no mechanism in the operating system that it's running that says, hey, we've got multiple cores here, it's just going to run on CPU 0 as if it's a single processor system, as if it's a single core system. So really, whenever we're talking about the ability to move to an SMP operating system, primary thing is we just need to make sure that the operating system is capable of handling more than one core, capable of identifying how many cores there are, capable of identifying the resources for each one of those cores. And so since this is done, and since the interactivity between these cores is through a shared memory, the operating system needs to have a little bit more oomph to it. I mean, if you think about it, a cluster operating system, the operating system that's handling a node in a cluster, and I know we haven't talked about clusters yet, but the system that is handling just a single node of a cluster, it really only needs to it needs to have libraries installed that allow it to pass messages to other devices. This is not so with an SMP. The operating system has some pretty significant responsibilities. So from the point of view of the user, you can't notice any difference. I mean, yeah, we've got the ability to, put the description of each one of the cores to the screen. We've got the ability to access certain applications which will show the performance of each one of the cores. But for the most part, when the user is in front of the machine, it's a single machine. All the operations, all the processes, all the threads, those are still being executed as they would be on a single machine, except in addition to time slicing. Remember when we talked about multitasking in the beginning, we were talking about how one process or one thread gets the processor for X nanoseconds or X milliseconds, and then we move to the next one. Well, now we not only are time slicing the activities, we're actually slicing them across all the processors. But for all intents and purposes, from the user's point of view, it looks like a single machine. Now, some of the things that are required, because there are multiple processors that are calling multiple operating system functions, the routines, and those routines, in order to save memory, we don't want to load a copy of an operating system routine for each one of the cores. We want to have one copy. But those copies need to be reentrant. In other words, I need to be able to have different cores call the same function in the same memory location. And this is as far as the location of the function or the routine. And this is, what are we doing? We need to make sure that those functions, those routines, don't get corrupted data or corrupted operation if two cores are executing them at the same time. In addition, whenever we've got multiple processors, we need to be able to have all of our tables, any of our queues, be able to also include which core the process is running on. So it is a lot more than just simply which processor we're going to execute at which point in time. It also is which processor it's being executed upon. So the basic ideas, the basic design issues we have to be concerned with are synchronization. So all the resources, now we need to make sure that if I have multiple cores using multiple resources, make sure that the resource is capable of identifying the core that's requesting the information or that has having the information given to that particular resource. Memory management, well, you know, we really have two ways of having pages now. We have first of all the level of privilege for a single core for a page, but now we also have this understanding of pages in virtual memory could be shared, and making sure that now not only is the privilege satisfied, but which cores are allowed to have access to pages. That is also now an important concern, a concern that is handled by the operating system. Also, there has to be some method of determining if a core or if a resource has gone bad. Earlier on I showed you that diagram where we had 4 cores and talked about how this is really helpful in terms of reliability, because if a core dies, well, in a symmetric multiprocessor system, all the other cores have the same capabilities as the core that died. Well, we need to make sure that the core that has died, that is recognized by the operating system for 2 reasons. Number 1, we need to make sure that any sort of responsibilities that had been given to that core, for example, portions of the operating system that were running on that core, or threads, processes that were running on that core, we need to make sure those are transferred off to a new core. The second thing is whenever it comes to assigning a new process or thread, we need to take that core out of the list of available cores. So how does the operating system detect that a core has gone bad? Well, we'll talk a lot more about this in the clusters lecture, but really what we're looking at is each core needs to send either a heartbeat, a signal saying, I'm still working, I'm still working, I'm still working, so that the operating system is aware that that core is still available. Sometimes the operating system does something called polling, where it actually polls and waits for a response from each one of these cores. Either way, we need to be able to detect when a processor has failed and make sure that it does not corrupt the operation of the other cores.